Hello, hello. So today I'm going to be talking about L'Hopital's rule with limits of quotients. So what that means is if we have a limit on the left side here, and we're taking the limit of a quotient like e to the x over x squared, how can we find that limit? Okay, so if we were to just plug in, as x approaches infinity, if we were just to plug in x equals infinity into this, we would get e to the infinity over infinity squared. Okay, so e to the power of infinity, that's just going to be infinity, because we're multiplying e by itself an infinite amount of times, and that's just going to be a super huge number that's never going to end. Okay, infinity squared, we're taking infinity, which is like an infinitely large number, and we're squaring it, so that's also going to be infinity. So L'Hopital's rule is used when we have a quotient, let's call it f, divided by g, and when we take the limit of that, if we take the limit as x approaches a, say some number, of f of over g, if we get 0 over 0, or infinity over infinity, that's called an indeterminate form. So if it's like 0 over 10, we wouldn't need L'Hopital's rule because 0 over 10 is just 0. Anything, or 0 over anything is just 0, unless it's just 0. So 0 over 0, that's indeterminate, we'd need L'Hopital's rule. Infinity over infinity, we'd also need L'Hopital's rule. So that's the case that you'd use that. Let's look at the case on the left here. Do we need to use L'Hopital's rule? Well, if we plug in infinity for x, we'll get infinity over infinity. So yes, we will use L'Hopital's rule and see if that helps. So this is going to be the same as the limit as x approaches infinity of the derivative of e to the x over the derivative of x squared. So what's that going to be? Well, the derivative of e to the x is e to the x. The derivative of x squared is just 2x. Okay, but notice if we were to plug in infinity for x here and x here, we'd still get infinity over infinity. So we have to differentiate the top and the bottom again. In L'Hopital's rule, you can keep using the differentiation on the top and bottom until you get an answer that doesn't give you an indeterminate form. So the derivative with respect to x of e to the x is still e to the x. On the bottom, it's going to be the derivative of 2x with respect to x, so it's just going to be 2. So now if we plug in infinity for x, we're going to get e to the infinity divided by 2. Okay, e to the infinity is infinity, and 2 is just a constant too. So anytime we have a number infinity dividing by a constant number like 2, that's just going to be infinity. Okay, because this infinity here isn't bounded by anything. It's just being divided by 2. But if you divide an infinitely large number by 2, it's still going to be that same infinitely large number. Okay, but before if we had infinity divided by infinity, that doesn't really mean anything because we don't really know like which infinity is larger. Okay, another way you can think about it is if we were to just think of how these two functions worked, e to the x gets super large super quickly as we move to the positive x direction. X squared, it still increases, but it increases at a slower rate. Okay, so as we go to the positive x direction, as x goes to infinity, e to the x is going to dominate the two functions. It's going to increase an incredible amount as we increase in our x values there. What we can also do is we can think about this numerically. So let's say we plugged in some pretty big number for x. So let's say we took e to the power of 100. So let's say we took e to the power of 100. That's 2.7 times 10 to the 43. So 2.7 times 10 with 43 zeros. Okay, 100 squared. That's 10,000. So we're taking a number with about 44 zeros, dividing by a number with 5 or 4 zeros. So you can see how this is going to go to infinity super quickly. Even as x is only 100, it's going to be a super huge number. Okay, so we can think about it like that with a calculator. Let's try this one. The limit as x approaches infinity of 3x squared minus 4x over 11 minus 6x squared. Okay, so if we plug infinity into here, we're going to get an indeterminate form. So let's take the derivative of the top and the bottom. So we get d over dx here. So this is going to be the limit as x goes to infinity of the derivative of 3x squared is 6x minus 4, the derivative of 4x, over negative 12x. Because the derivative of a constant 11 is just 0. Okay. Now, if we plug in infinity for x here, we're going to get 6 times infinity, which is infinity, minus 4, which is still infinity, over negative 12 times infinity, which is negative infinity. So this is infinity over negative infinity, which is an indeterminate form. So we have to use L'Hopital's rule again, because we can't just substitute in the x. So if we differentiate the top and the bottom, right, we take d over dx here, d over dx here, it's going to be 6 over negative 12. And this simplifies to negative 1 over 2. So this number here, this fraction, there's no x to substitute in infinity with. So we just get a number, that's going to be our limit. So as this function here gets super, super big in the x direction, it's going to go to negative 1/2 in the y values. Okay, another way we can think about this is as x gets super, super, super big, the 11 and the 4x, okay, the 11 and the 4x, those don't matter as much anymore, because these x squareds are the dominant components of the function. So all we're thinking about now really is the limit as x goes to infinity of 3x squared over negative 6x squared. Okay, and the x squareds cancel here. This is just going to be 3 over negative 6, which is negative 1/2. So for this one, we didn't have to use L'Hopital's rule, because we can imagine these are two polynomial functions. As x gets super big, these ones are going to dominate, and we can just kind of analyze those. Okay, let's look at the limit as x approaches 3. Pardon me, still getting over this nasty cough here. Of x squared plus x minus 12 divided by x squared minus 17x plus 52. Okay, so for this one, let's see, if we were to plug in 3 for x, this would be 3 squared plus 3 minus 12 over 3 squared minus 17 times 3, that's going to be, what is that, 34, 51, so minus 51 plus 52. Okay, this is going to be 9 squared, so that's going to be 0. 3 squared minus 51 plus 52, that's going to be, what is that, 9 squared, sorry, so that's 9 minus 51 plus 52, so this is 9 minus 51, that's going to be negative 42 plus 52, so that's going to give us positive 10. So this limit's going to be 0. We don't even have to use L'Hopital's rule, because when we plug in 3 for x, we just get 0 over 10, so the limit's just going to be 0. Okay, the limit as x goes to infinity of the square root of x plus 1 over e to the 2x. Okay, if we were to plug in infinity for x here, we're going to get the square root of infinity plus 1, which is infinity, over e to the power of 2 infinity, which is infinity as well. So this is an indeterminate form, because we have infinity over infinity. Okay, so let's use L'Hopital's rule. Let's differentiate the top and the bottom. So this is going to be the limit as x goes to infinity of, well, the square root of x plus 1. That's the same as x plus 1 to the power of 1/2. So we can bring that 1/2 out front using our power rule and reduce this exponent of 1/2 by 1. So that's going to be negative 1/2. So this is going to be negative 1 over 2 root x plus 1. Okay, so 1 over 2 root x plus 1 divided by the derivative of e to the 2x is just e to the 2x times the derivative of the exponent using the chain rule. So that's going to be just 2e to the 2x. Okay, if we simplify this a little bit, we're going to get 1 over 4e to the 2x, because it's 2 times 2, we're bringing these to the bottom, and then square root x plus 1. So this is going to be 1 over 4e to the 2 infinity square root infinity plus 1. And that's going to be 1 over infinity, which is just 0. Okay, another way we can think about it, we did it in a previous question, is if we look at how the square root function increases, it looks like this. E to the 2x looks like this. So while both of them are increasing, the square root is increasing at a decreasing rate. So e to the 2x is going to be the dominant component of this function. So as x gets super big, we're going to get an infinitely big number divided by a number that's just like, or sorry, we're going to get a number that's basically like some constant as it flattens out divided by e to the 2x, which is an infinitely big number. And that's what we see down here. So that's why our answer is going to be 0. So our answer is going to be 0 here. Okay. We can think about it like that because e to the 2x, this function is called being bottom heavy. So this is a bottom heavy function because the bottom of our fraction is going to dominate the top of it. Let's say it was e to the x over, say, x cubed. E to the x increases like this, x cubed increases like this. So e to the x is our dominant function. Anytime we have an exponential, it's always going to, like, at some point, dominate a polynomial function as x gets super big. So this is going to be top heavy. Anytime we have a top heavy function and we're taking the limit as x goes to infinity, that's just going to be infinity. Okay. So the last one here. The limit as x goes to 0 of sine of x over x. Okay, if we were to plug in 0 here for x, we would get sine 0 over 0, which is 0 over 0. And that is an indeterminate form, so we're going to use L'Hopital's rule. Okay, so if we differentiate the top and the bottom with respect to x, we're going to get the limit as x goes to 0 of the derivative of sine x is cos x divided by derivative of x is just 1. So now we can substitute in 0 for x. We're going to get cosine 0 over 1. Cosine 0 is just 1. So we're going to get 1 over 1, which is just 1. Okay. And the what this function looks like is, if we are to axes here, the function looks like this. It obviously the limit at 0 is 1, like we just figured out. And it's going to go down like a sine function or cosine, and then it's going to flatten out. And as x gets super big or super small, it's going to kind of flatten out to 0. It's going to look like this. Okay, so we found the limit as it approaches 0. Let's try finding the limit as it approaches positive infinity. We can see it's going to be 0, but let's see if we can figure that out using L'Hopital's rule. So let's just erase this here. Let's take the limit as x approaches infinity. Okay. So if we were to plug in infinity for x, we would get sine of infinity over infinity. Okay, because the sine function is a periodic function, meaning it repeats its pattern over a certain period. So sine functions always look like this, right? They repeat themselves, and they're always between +1 and -1. So the sine of infinity, we don't know exactly what that is because infinity is not a number, but it's going to be somewhere between 1 and -1. So we're taking a number, let's just call it, like, at the most, it's going to be 1. That's the most positive case, divided by infinity. And this is just going to be 0. So we can think about it like that, but what if we use L'Hopital's rule? Well, if we use L'Hopital's rule, that would have to mean that this is an indeterminate form as we plugged in infinity for x. So since sine of infinity over infinity isn't an indeterminate form, it's 1 over infinity, we can't use L'Hopital's rule because we just got our answer by plugging in infinity. By substituting in infinity for x, we know that this is going to be 0. We can also prove this using the squeeze theorem, which I'll talk about later, but that's kind of the main idea for this one. So L'Hopital's rule is just when we have some limit and we substitute in the x value it's approaching into the function, right, or the expression, and we get an indeterminate form, 0 over 0, or infinity over infinity, we can differentiate the top and the bottom of the fraction and analyze it further from there. Okay, in my next video, I'm going to talk about finding or using L'Hopital's rule to find limits of products. So for example, x times the natural log of x, that equals what as x approaches, like, say, infinity? How can we figure that out? Okay, we're going to use a similar method. It's just going to be kind of one more step. Okay, so I'll see you in my next video, and I hope this was helpful.